Alright, let's just finish off this last question. So, I know that when I look at this question, it seems like there's not much information here, right? I know that the half-life is 1600 years, and I want to find how long it will take so that the mass is 1/3 of its original, knowing that its rate is proportional to this rate of change is proportional to its mass. When I'm looking at these questions, these applications of calculus to these, situations, right? I'm really looking for keywords. If I'm not given an equation, I want to think about what other information I'm given. And I know that its rate of change is proportional to its mass, so I can assume that there's an exponential rate of change. In this case, we're looking at decay, right? Because we're looking at half-lives of isotopes. So I can assume that I'm going to have some form like this. Right? I know that m, the mass of this object, is going to be equal to m sub 0 e to the kt, where this is the initial. Okay. I guess the hardest part in this question is that I'm not really given any initial mass. So I have to think about what are the info I'm given. Right? I know, though, that its half-life is 1600 years. And obviously half-life, that's how long it takes to get to half of its mass. How can I use that information? Well, because it's a function of time, I know that when t is equal to 1600, so how many years, right? My m value, I think, what's that going to be equal to? Well, my m value, that would just be half of what I started with, because it's its half-life, obviously, right? What do I start with? Well, I don't know the value, but I know that the initial amount is m0, right? So I could say half m0. Okay. How can I use this information now? Well, if I go back and see the question I'm trying to answer, I know that I want to find out how long it takes for the radium to be 1/3 of its original mass. And we decided that, or we realized that it should be in between 1600 and 3200 years, because if its half-life is going to be every 1600 years, then obviously it has to be in between these two values here. And we kind of guessed, maybe somewhere in between there. Maybe it's about halfway, since 33.33% is around halfway there. Okay. How close are we? Well, let's have a look. So before I go any further and try and answer the question, I'm still missing a lot of information, right? I know I can fill in values for t and m, but I don't know that growth constant k. I don't know that value there. What I want to do is try and use this information here to find it. I can substitute in those values I know. I know that when m is equal to half m0, and when t is equal to 1600, then this equation is true, right? All I've done is substitute in those values. Now that I have something like this, it's really easy to solve for k, because I can divide through my constants here. Now you notice that these m0s, I'll just divide through, right? So I'll have half is equal to e to the power 1600k. When you have a situation like this, you really want to be trying to solve for k using your natural logarithms, right? Because you've got base e here, so I'll take the log of both sides. And now using your log laws, you know that I can just take this power down as a coefficient, and then I'll be left with ln of e. Well, ln of e, that's just 1. So really I'll have ln of half is equal to 1600k. And then solving for k, I'll just divide both sides by 1600. Okay. So far so good. Now I'm not going to evaluate that just yet, because usually it's going to be a long decimal, and I still haven't really answered the question yet, so I'm just going to park that for now. Let's come back to what the question is actually asking. I'm looking to find out how long it takes for the radioactivity to be 1/3 of its original. And now, I know from looking earlier when I was looking at these half-lives, if I had another 1600 years pass, a long time, right, I would get to 25%. So we realized that the amount of time it takes to get to 33.33% has to be somewhere in between there. And we guess, well, maybe it's around 2400. That's about halfway. Let's see how close we were. Using this information now, I can go back to my original equation here, and then substitute the values I know. I know I'm looking for now, not when m is equal to half of m0, but when it's equal to a third of its original. So I want when m is equal to a third of m sub 0, right? All I'll do is go into my equation and substitute that value. So the third of m sub 0 is equal to m sub 0 e to the kt. I'm just going to leave the k for now because, yeah, it's like a long expression. Don't really want to chuck that in here just yet. I can divide through my m sub 0's again. I'll get 1/3 is equal to e to the kt. And same idea. Let's take those natural logs. I'll just skip it straight. I'll go straight to dropping the power down. I'll just get left with kt. And that now it's really easy to solve, right? Remember, the question is asking how long will it take? And I'm really trying to find that variable t. So I'll just divide both sides by k. Remember k, well, that's just this guy over here. And that's when I write in what my k value is. Let's just calculate that quickly. And we're pretty close. So it takes about 2,543.94. So let's just round that. 2,544 years. Okay? So you saw that when I was looking at this question, it didn't initially seem like there was much information, right? But when we break it down, when I realized that this is just an exponential decay question, I can use this equation to find out how long it takes to be a third of its original size.